Heisenberg's uncertainty principle states that you cannot know precisely the position and the momentum of a particle at a given time. The probability of finding an electron at a particular position is the greatest at the nucleus, but more electrons can fit in the outer rings, so the probability increases to a point the further away from the nucleus that you get. The off-ball principle states that as protons are added to the nucleus, electrons are added to the orbitals at the lowest energy first. Hund's rule says that electrons do not pair up until they have to. So first it'll enter the lowest energy, according to off-ball, and then it's got to pair up before moving on to the second energy level. When it comes to the 2p, it has 3 orbitals that it can put 1 in each of them before they have to pair up. After it's completely paired, then it can go on to the next level. Valence electrons are the electrons in the outermost principal quantum level. It's usually only considered s and p orbitals. To determine the electron configuration using the periodic table, you need to know your s, p, d, and f blocks. So first you have the s blocks, then the d's, and then the p's, and at the bottom you have the f's. Notice that the s and the p's are the same as the period number, while the d's are 1 less than the period number, and the f's are 2 less than the period number. The s block can hold 2 electrons at most, and it has 1 orbital. The p's can hold 6 electrons, and it has 3 orbitals. Each d can hold 10 electrons, and it has 5 orbitals, and the f's can hold 14 electrons, and there's 7 orbitals. So if we're to find the electron configuration of sulfur, the first thing we need to do is find it on the periodic table. So to get to sulfur, we go through the 1s, we go through it completely. So that's 1s2, then the 2s2, we go all the way through 2p, so it's 2p6, 3s2, and then 3p4, because we stop at the 4th one. Notice the superscript is telling us how many electrons are in that energy level. Try cadmium on your own. Restart when you have it done. Cadmium, you should have gotten 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and 4d10. For sodium plus 1, we lost an electron, which means it's the same as neon. So you just write the electron configuration for neon. Go ahead and pause the video and restart when you have it done. You should have 1s2, 2s2, 2p6. Fluorine minus 1 gained an electron, which means it's also the same as neon, meaning it has the same configuration. When we want to write the kernel electron configuration or shorthand configuration, we need to look and see what's the noble gas before that element. So for HF, we look and krypton is the noble gas before it. So we're starting at krypton and we need to put that in brackets. And then we're going to start there. So that's 6s2, 5d1. Then we're going to go to the F's and we're going to go all the way through the 4F's, so that's 4f14. And then we have one more D. You can write it this way, or you can combine the D's and put krypton, 6s2, 4f14, and 5d2. Either way. Go ahead and write your shorthand configurations for radium and lead. Restart when you have your answer. So for radium, you should have had xenon and then 7s2. For the lead, you should have had xenon, 6s2, 4f14, 5d10, and 6p2. Nickel plus 2 is a little bit trickier, so let's write out nickel's regular configuration. Or it's shorthand, but just for nickel atom. You have argon and then 4s2, 3d8. So if it's nickel with a plus 2 charge, it's going to lose its valence electrons first. And remember that we'd said the valence electrons are the s and p orbitals. So it should lose its 4s before it loses its 3d, because the 3d is closer to the nucleus, which means it's attracted to the nucleus more. So we have argon and 3d8. If it had been a nickel with a plus 3 charge, it would have been 3d7. Some exceptions to the octet rule are chromium and copper. Chromium should have the configuration, if you look at it, 4s2, 3d4. But it's lower in energy and more stable if it moves one of those 4s electrons to the 3d, giving it 4s1, 3d5. The same thing's going to happen with copper, where it should have been 4s2, 3d9. It's going to lose that electron in the 4s and move it to the 3d. Go ahead and pause the video and figure out what element this represents. So you can add up your electrons. You can also follow it 1s2, 2s2, 2p6, 3s2, 3p3 should be phosphorus. It says, which of the following is an excited state? An excited state means that an energy level was skipped. Be careful because some are just out of order, but they're not skipped. Go ahead and pause the video and see if you can figure out the excited state one. In A, we have 1s, then 2s, then 2p, then 3s, then 3p. There is a 4s, and then a 3d. It's out of order, but it's still all there. A lot of times you'll see it written this way on multiple choice problems because they group the 3s and the 4s together. So A is not excited, just out of order. In B, everything's there. In C, we have 1s, 2s, 2p, 3s, and there should be a 3p there, but there's not. And always look at all your answers. D is all there, so our excited state was C.